Hello friends, welcome to H3 Web and Academy. In the last lecture, we have completed the discussion on the constraints and its types. So in this particular lecture, we will discuss about the Hamiltonian principle. The Hamiltonian principle is also known as integral principle or principle of least actions. Let's start our discussion. So अभी तक आपने complete course का subscription नहीं लिया है तो नीचे दिए गए नंबर पे कॉल कर सकते हैं. Okay. The Hamiltonian principle is based on the concept that whenever a particle move from point A to point B, follows that path. It follows that path on which the efforts are minimum. So let us take there as n number of path for traveling from point A to point B. As per Hamiltonian principle, it is the tendency of the particle to choose that path on which the efforts are minimum. So let us take this as path 1, path 2, this as path n, path. Okay. So as per Hamiltonian principle, the particle will choose that path on which the efforts are minimum or action taken is of minimum value. Okay. We have that, then that path is known as actual path. Actual path equal to path chosen by the particle along which efforts are minimum. Efforts are okay, or action taken minimum value. This is our actual path. We can relate this with day-to-day activities also. Suppose we want to move from place 1. Suppose we want to move from Patna to Gaya. So we will choose that path on which the time consumed is less. This is obvious, na? Okay, so we want to minimize the time. Minimize. Okay. So let us go back to the definition. The motion of a system from time t1 to t2 such that the line integral, also known as action or action integral, has a stationary value for the actual path of the motion. So the actual path is path chosen by the particle along which the efforts are minimum. So there are n number of paths. So the particle will choose that path on which the efforts are minimum. So let us take this path as the actual path. This is our actual path. Along this path, the efforts are minimum. We have assumed this. Okay. The actual path is the path chosen by the particle along which the efforts are minimum. Okay. So as a stationary value for the path of the motion or variation of line integral is 0. Let us find this action. How we can find this action or action integral? Action or action integral. How we can find this? Action integral is represented by I. I is our action or action integral. Action integral. Okay, so how we can find the action integral? When the difference of kinetic energy and potential energy is summed over the entire path of the actual path. Okay, summed over the entire path of the actual path from time t1 to, this is basically our action or action integral. As per Hamiltonian principle, along the actual path, the value of this I is constant, or variation in this value of I. Variation in the value of I is 0. It is obvious. Something is constant, then the differentiation of that is of 0. Okay. So we have the action integral as constant as per Hamiltonian principle. This is the basic definition of the Hamiltonian principle. The motion of a system from time t1 to t2 is such that the line integral has a stationary value. Okay, so this is our line integral. Because we are taking this particular path, we are integrating the difference of this value t minus v along this path, because this is our actual path, has a stationary value. So this is constant, that is a stationary value, or variation in the line integral is 0. So this is variation in the line integral is 0. Either it is constant or variation in tan integral is 0. The axial integral is given by I is equal to L dt constant. So this is basically L. Okay, so L we can represent as L is equal to T minus V. L is the consist of the L consists of our generalized coordinate and generalized velocity, and there is some time also there. This is basically our Lagrangian. So L is equal to T minus V. L can be represented in terms of the generalized coordinate, generalized velocity, and sometimes time also. This is our Lagrangian. Okay. So we have the axial integral is either constant or it has a the variation in the value of axial integral as 0. Based on this concept, there is a derivation of this Euler's Lagrangian equation. Derivation is not so important, so we can directly deal with this expression, that is del L upon del Q minus d upon dt of del L upon del Q dot. So Q dot is the generalized velocity, Q is the generalized coordinate, okay, and L is the Lagrangian, which is equal to T minus, Lagrangian is equal to T minus. Okay, so let us discuss some questions on this. Based on this, we can directly, rather than moving on the derivation part, because that is not relevant to the exam, so we will directly go to the question, solving questions. So let us solve questions on the Euler's Lagrangian equation. Okay, that is the most demanding area of the UPSC. Okay, generally the questions are asked on this principle. Okay, Euler's Lagrangian equation. This is not so important, but this is very important. Okay, lots of questions are being asked on the Euler's Lagrangian equation. Let us start discussing the problems. Okay, so let us discuss problems on Euler's Lagrangian equation. So what is given in the question number 1? Derive Newton's second law based on the motion of point mass particle experiencing a potential energy V using the Lagrangian equation. Okay. Also, this question can be framed as show that Newton's second law is equivalent to Euler's Lagrangian equation. So how we can solve this? So let us take a point mass particle. Okay, mass particle experiencing a potential energy V. So let us take the velocity of this particle as V. Okay, and we are assuming that it is a 3D space. Okay, so let us take the coordinates of this particle as x, y, and z. This particle is moving as velocity v. So v can be written as v is equal to x dot I cap plus y dot j cap plus z dot k cap. Okay, so x dot is the velocity along x direction. So x is equal to x dot, vy is equal to y dot, and vz is equal to z dot. Okay, so what is the Euler's Lagrangian equation? We have the Euler's Lagrangian equation as del L upon del Q minus d upon dt of del L upon del Q dot is equal to 0. Okay, and Q is the generalized coordinate and Q dot is the generalized velocity. Okay, so we have the generalized coordinate as x, y, and z. Okay, so there will be 3 cases. Okay, so the Euler's Lagrangian equation in terms of x as the generalized coordinate, Euler's equation in the terms of y as a generalized coordinate, Euler's equation in terms of z as a generalized coordinate. Okay, so let us find the L first. Okay, so the L is equal to T minus V, where T is the kinetic energy. So T is equal to V is the potential energy. Okay, that is given in the question. So T is equal to the kinetic energy. So kinetic energy is equal to half m into V square. This we can write as V square is equal to Vx square plus Vy square plus Vz square. This can we can write as Vx is equal to x dot x square plus y dot square plus z dot square. This is the kinetic energy, and let us keep V as it is. V is the potential energy. So our Lagrangian will be L is equal to T minus V. So half m to x dot square plus y dot square plus z dot square minus of potential energy. Okay, so let us calculate this. So we have this as Lagrangian equation in terms of x. Okay, let us write down here. So we have the Lagrangian as half m x dot square plus y dot square plus z dot square minus of v. Okay, so we have the Euler's Lagrangian equation as Lagrangian Euler's Lagrangian. This is del L upon del Q minus d upon dt of del L upon del Q dot equal to. Okay, so we have the values as terms of x, terms of y. Okay, so let us find these. After that, we will take in terms of z. Okay, okay, so we have in terms of x as we have x as a generalized coordinate, so we will put q is equal to x. Okay, and q dot equal to x dot. So we have del L upon del x minus d upon dt of del L upon del x dot is equal to 0. Okay, so let us find del L upon del x. So del L upon del x, so there is no term of x here, only will be minus del v upon del x. So minus del v upon del x minus d upon dt of del L upon del x dot. X dot is here only. So this is half of m to 2x dot. Okay, this is equal to 0. This is equal to minus del v upon del x minus d upon dt of, this gets cancelled. This is m into x dot. Okay, equal to 0. So from here we have minus del v upon del x is equal to d upon dt of x dot. Mx dot, m times of velocity. So this is the momentum along x direction, and this value is fx, force along x direction. Fx is equal to negative derivative of the potential with respect to x. V is the potential energy. So negative derivative of potential energy with respect to x will gives the force along x direction. So this is Fx is equal to d upon dt of differentiation of momentum along x direction. Okay. Similarly, from here we have del L upon del y minus d upon dt of del L upon del y dot equal to 0. So del L upon del y. So there is no term of y here. Only will be minus del v upon del y minus d upon dt of del L upon del y dot. Y dot is here. This is half of m 2 y dot equal to 0. So this gets cancelled. Minus del v upon del y equal to d upon dt of m into y dot. Okay, so mass into velocity. So this is the m y dot is the momentum along y direction, and this is force along y direction. So f of y is equal to d upon dt of momentum along y direction. Similarly, in case of z, fz is equal to d upon dt of momentum along z direction. Okay, so we have let us write down this in the terms of vector notation. We have fx I cap plus fy j cap plus fz k cap is equal to dpx upon dt to I cap plus dpy upon dt into j cap plus dpz upon dt k cap. Okay, so this is nothing but Newton's second law. Newton's second law. Okay, so force is equal to d upon dt of momentum. So px is the momentum along x direction, py is momentum along y direction, and pz is momentum along z direction. This is solution of question number 1. So we have derived Newton's second law of motion from Euler's Lagrangian equation. Let's discuss question number 2. How we can solve this? What is given in question number 2? Find the distance traveled by particle falling under gravity after time t using Euler's Lagrangian equation. What is Euler's Lagrangian equation? This we have already discussed. We have the Euler's Lagrangian equation as del L upon del Q d upon dt of del L upon del Q dot is equal to 0. Okay, so we have to find the distance traveled by particle falling under gravity after time t. How we can find this? Let us just take a particle here. The initial position of the particle. The position of particle, let us consider is the ground level. Ground level. At a height of that ground. This is the ground level. The initial position of the particle is at a height h from the ground level. This is the position of the particle at time t is equal to t and t is equal to 0. Let us take the reference along this direction. Let us take y as the generalized coordinate. This distance is, let us take at a distance y from the initial position. The initial position is at a distance y from the initial position. So we have Lagrangian as T minus V. T is the kinetic energy. What is the kinetic energy at time t is equal to 2? Half m into v square. Velocity along this direction will be y dot square minus the potential energy. What will be the value of v? The potential energy is equal to, we are taking reference from here. This will be m times mg to this distance. This distance is h minus. So we have this as the Lagrangian as t minus v is equal to half m to y dot square h minus equal to half m y dot square minus h plus g into y. This is the Lagrangian. This is equal to, let us take this as constant. This is capital A. Let us take this as constant. L is equal to half m y dot square plus mg into y plus constant. Let us apply the Euler's Lagrangian equation. So we have the value of L as L is equal to half m y dot square plus y plus constant. We have the Euler's Lagrangian equation as del L upon del Q minus d upon dt of del L upon del Q dot equal to 0. Okay, so we have the generalized coordinate q is equal to y here. Let us replace q with y and q dot with y dot. Replace this y and this y dot. Okay. Let us further simplify this. So we have the value of del L upon del y. So there is no term of y in this term. See, the term of y is in this particular term. This is mg minus d upon dt of del L upon del y dot equal to half m y dot is equal to 0 minus m into dy dot upon dt equal to 0. We have dy upon dt equal to g. Okay, this is dy upon dt. So from here we have d of, let us integrate this. This we can further simplify as d2y upon r is equal to g. This we can write as, because y dot is dy upon dt. Y is equal to dy upon dt. d upon dt of y dot is equal to d2y upon dt. Okay, so let us integrate this. So we have dy upon dt equal to gt plus constant of integration. Let us take this as b. Okay, so now at t is equal to 0, t is equal to 0 at the initial position, the final position. This distance is y. This is at t is equal to 0 and t is equal to t. So at t is equal to 0, the initial velocity is 0. dy upon dt is equal to 0. So from here at t is equal to 0, dy is equal dy by dt is 0. So this is 0. From here b is equal to 0. We can neglect this. Now let us further integrate this. We have dy is equal to dt into d. Here y is equal to dt square upon 2 plus constant of integration. Where t is equal to 0, we have t is equal to 0, y is equal to 0. So from here we have 0 is equal to 0 plus c. From here c is equal to 0. So we can neglect this term. The distance traveled, we have to find the distance traveled by the particle after time t. The distance traveled after time t is given by half gt. Okay. Now let us discuss question number 3. Okay, so let us discuss question number 3. Find the acceleration of a at-wood machine consisting of masses m1 and m2. m1 is greater than m2, pulley of mass mp, radius r, length of the string is l. So how we can solve this? So let us draw a pulley first. Let us draw a pulley. So we have a pulley like this. It is of a radius r. There is string. Pulley consists of a string of length l that is running over it. Consists of two masses of m1 and m2. Masses are there. m1. Let's take this as a reference point. Our reference. Since this radius is r, so this whole length will be pi r. Pi r. Let us take this distance as x from the reference, from the center of mass of this particle m1. Let us take this. Okay, so we have the coordinates here as, let us take this distance as y for the time being. We have the coordinate here as x and y, that are the variable, and we have constraint. Only one constraint is here, that length of the string is constant. So we have coordinate as x and y, and constraint is 1. The number of coordinates are 2, constraint is 1. So the generalized coordinate is 2 minus 1 is equal to 1. 1 is the generalized coordinate, that is x. So we can represent y in terms of x because we have constraint here, that is length of the string is constant. Let us represent y in terms of x. So we have x plus this distance, half of the circumference, pi r, plus y is equal to length of the string. We have y is equal to l minus x minus pi r. Y is equal to l minus x minus. Okay, and we have m1 is greater than m2. This will go down, this will go up. Okay. Since the length of the string is constant, it is not changing. Okay, it is, so in the question it is given that m1 is greater than m2. Since m1 is greater than m2, 1 will come down, 2 will come up. Okay. Since the length of the string is constant, so the velocity with which 1 will come down, same velocity m2 will go up. Velocity with which m1 will come down is x dot, change in value of x with respect to time. This velocity will be same velocity. We have the kinetic energy T as, let us take this of m1. So half m1 x dot square plus half m x dot square. We have the rotation energy of this pulley. Okay, so this is of radius r. So we have this as half of I theta square. This is the rotational energy. We have I is equal to, this is the disk actually, half into mp into r square. Okay. Theta is equal to sorry, this is theta dot square, half m omega square, no, theta dot square. The rotational angular velocity will be in direction because this is coming down. Angular velocity is equal to d theta upon dt. This theta dot. Omega is equal to v upon r. So the velocity is x dot. So this dot upon r. This we can replace as dot upon r ka the rotational energy. This is equal to T is equal to half 1 plus m2 x dot square plus half I omega square. Half into moment of inertia is half into p into r square dot square upon r square gets cancelled. We have this as T is equal to half 1 plus m2 dot square plus T upon 4x dot square. This is the kinetic energy. Now let us find the potential energy. Let's write down the kinetic energy here. We have the kinetic energy T is equal to half of 1 plus m dot square plus dot square upon. Okay. Now let us write down the potential energy. So we are taking, this is reference point. So distance, we are taking the distance above the reference point as positive. Distance below the reference point, because potential energy is we write the potential energy in with respect to the reference point. This is our reference point. Let us write down the potential energy. Potential energy of system. Okay, so we have three bodies to take into consideration. First one is m1, second one is, third one is the pulley of mass m. The pulley of mass mp is on the reference point. Potential energy will be 0 for mp, and for the mass m1 it is minus, because we are below the reference point. Minus of m1 into g into x. For this we have minus of m minus x, as simple as that, equal to minus of minus 1 plus equal to m2. This whole terms is constant, plus constant is capital A. Okay, the potential energy. We have the Lagrangian as L is equal to T minus V is equal to, let us write down, let us rub this is not required further. We have Lagrangian as T is equal to, Lagrangian as L is equal to T minus V, half of 1 plus m dot square plus dot square upon 4 minus V minus 1 x minus L is equal to half 1 plus m dot square plus dot square upon 4 plus 1 minus x minus. Okay. From here we have L is equal to half of 1 plus m x dot square plus dot square upon 4 plus 1 minus m x plus b is equal to minus 6. Okay. So now let us apply the Euler's Lagrangian equation. We have the Euler's Lagrangian equation as del L upon, here the generalized coordinate is x. We have del x minus d upon dt, del L upon del x dot equal to 0. Del L upon del x will be equal to 1 minus 2 into and minus of d upon dt of del L upon del x dot. So it will be half of 1 plus m x dot, okay, x dot upon gets cancelled. This gets cancelled with, we have this as m1 minus is equal to 0, m2 equal to d upon dt of plus m, let's take x dot outside, d upon 2 dot, okay. So this is, let us further simplify this. Let us take this, this is constant, so let us take this out. 1 minus m to g equal to times of 1 plus p upon x double dot. From here x double dot equal to 1 minus m upon plus m. Okay, so this is the required acceleration of an Atwood machine. Okay, so we will discuss further questions in next particular. Thank you.